Greetings. Welcome to my Laplace transform video lecture series, Module 4. We'll start our video lecture series with an intro to Laplace transform and what a transform is in general, and then we'll proceed to doing Laplace transform and inverse Laplace transform, and then ultimately the convolution. Laplace transform is one of the most popular integral transforms that is used by the engineering and the science world to tackle differential equations. I have a general use of integral transforms or just typically integral transforms in general. Mathematical notation aside, the motivation behind integral transform is easy to understand. There are many classes of problems that are difficult to solve, or at least quite unwidely algebraically, and in their original representations. An integral transform maps an equation from its original domain into another domain, manipulating and solving the equation in the target domain, which could probably be easier than doing it in its natural domain, and then ultimately achieving a solution. Basically, instead of solving a differential equation, if you apply the transform to the differential equation, it has the ability to converting the differential equation into an algebraic equation, and then you could solve for y of x algebraically, which is much easier than doing it in a differential equation setting. And then once you get the answer, you do a Laplace inverse and take it back to the original variable that the differential equation was about, let's say time domain, so you find the solution actually in time domain. Areas of application is quite wide. It's in the field of mechanical vibration, heat conduction, potential theory, mechanics of solids and fluids, probability theory and statistics, hydrodynamics, elasticity theory, and so on and so forth. A working knowledge in any of these areas is generally sufficient to work examples and exercises. And here I have shown you guys, in general, when you take the general transform of a function, say in variable u, then by some definition, a transform of some function has always been defined by an integral of that function multiplied by what's called a kernel, which is actually making the transformation possible into a new domain or into a new variable. Now, there's a lot of transforms, and I've given you a list of the most famous ones, but we are primarily interested in Laplace transform, which is used to solve continuous cases, hence differential equations. Now, if you have a discrete case, then the transform that's used has to be discrete-based transform, which is known as Z transform. If you're doing partial differential equations, then you want to use the Fourier transform. So there are a lot of different transforms, but we're going to focus on the most famous transform known as the Laplace transform. Now, what to expect? The basic aim of a transform method is to transform a given problem into one that's easier to solve, as I said. So the concept is, again, we have a differential equation, we apply Laplace transform to it, it has the potential of turning that into an algebraic equation, we solve for the solution, and then do a Laplace inverse to take it back to time domain. In the case of an ODE equation with constant coefficients, the transform problem is algebraic, again, as I said. The Laplace transform is basic to the solution of initial value problem, and you guys could read the rest. So, introducing us to Laplace transform, it was introduced by Pierre-Simon Laplace in his work on probability theory, so that's what it came out of. It resolves a function into its moment. The Laplace transform is often interpreted as a transformation from the time domain, in which the input and outputs are functions of time, to the frequency domain, which the inputs and outputs are a function of frequency. So again, as I said, Laplace transform takes a derivative or a differential equation, converts it into an algebraic equation in terms of variable s, known as the frequency domain. You solve for the solution, and then you inverse Laplace it to get the actual time domain solution. All right, now I've introduced this to you guys on our face-to-face Zoom discussion, but I just wanted to iterate that Laplace transform that we have seen by definition of a function, f of t e to the minus st dt, definition of Laplace transform, actually didn't come to someone in their sleep. It actually comes from the very simple concept of power series. Now, if you have a power series, and obviously you'll be looking for a sub n's, if you take that and you've converted to a sort of a computer notation, so instead of a sub n, you write a of n. Instead of a of n, you use some functional value, f of t, and also convert x to the n to some exponential form. If you do that, it's very interesting, and I've already shown this to you. So an is written as a of t, just like a functional notation, or f of t. A of t is the same thing as f of t. See how it transforms. X to the n part of it, you could write x as e to the ln of x. Then you could raise both sides to t. If x to be between 0 and 1 for this thing to converge, then the natural log of x has to be negative. So if, instead of writing ln of x, I could just use some negative entity, call it s. So you could see how this power series notation, if you want to write it as an integral notation, could actually turn into some kind of a definition that looks like this, which is the actual definition of Laplace transform. So it doesn't come from air. It actually comes from the fundamental definition of power series. Now, the idea is that we use Laplace transform as a definition to solve differential equations, and to also be able to find the solution and then use inverse Laplace transform to find the solutions of that differential equations. And in order for us to begin, we must first talk about some definitions of Laplace transform and their linearity. And that will be our next video lecture. Thank you.